Let's start this special conference on network economics, and I will give. Frank is going to say a few words about the origin of this workshop.
Thank you. Thanks, everyone. Well, look, it's a great pleasure to be here. The Georgetown Global Economics Challenge Network. It's an initiative of the President's Office at Georgetown, and so we have a number of partners. We've had a number of conferences on a wide variety of topics. I invite everyone to have a look at them. They're on the website. This may come as a surprise to you, but this is the fourth event that I've had in Paris at Sciences Po, because a very prominent partner was Sergey, who now unfortunately departed. But before Sergey decided to leave, we invited Matt, and Matt very graciously accepted to come. So it's a great pleasure to have Matt here. So thanks, Matt, for coming. Of course, when Sergey left, we needed someone to replace him, and Jean-Marc has done a tremendous job. So Jean-Marc, thanks for all your work. I very much appreciate it. So on behalf of Jean-Marc and myself and Georgetown, thanks very much for attending, and I look forward to a very interesting day. Thank you.
Okay, so I should stay close to here. You can ask questions whenever you want, except there's only 1 hour.
You can ask questions into the microphone.
Yes, so the microphone is over there. So this is joint work with. The specificity of this conference is that we have Matt speaking this afternoon, and the other papers are co-authored, at least by members of the department. Hopefully all related to network economics. So this paper is about the estimation of two-way fixed effect models. So I suppose you all know what is a two-way fixed effect model, but let me remind you. So there's going to be a model where the dependent variable is indexed by three indices. So I is, so there are two types of units. So typically here, workers and firms. So I would be the index of a worker, J would be the index of an employer, and T would be this particular observation for this particular match. And so for all ij, there is a certain number of wage observations. So a certain number of wage observations, which is denoted dij. So in labor, the interest for this model certainly started with this paper by John Abbott, Francis Kramer, and David Margolis, which was, and this paper was the first paper using match employee-employee data. That is allowing, these are registered data, administrative data, covering the universe of wages. At the time, so it was in France. Nowadays, these data are everywhere, and so the main application is to decompose the variance of cross-sectional variance of wages into the contribution of worker heterogeneity, the contribution of firm heterogeneity, and the residual, etc. So variance decomposition. In terms of identification, if the network of workers and firms is made of many sub-networks, you're going to need one normalization of worker and firm effects for each subgraph. So the usual practice is to keep the biggest connected subgraph. But that's not, even if you take the biggest connected subgraph, there's still a problem that remains, which is a weak identification problem that was studied in particular in this paper by Koen Mans, a former assistant professor of the department, and Martin Weidner, who studied, who show, who relate the bad performances of OLS estimation and they relate it to the fact that the network is such that you have one connected components, but I mean it's weakly disconnected in fact, and so there are subgraphs which are connected, but connected by a small number of links. And what paper by Zhang and Roe proved at about the same time is that in any sparse heterogeneous network, then the number of bottlenecks, that's how it's called, I mean this small number of links connecting two subgraphs, the number of bottlenecks tends to grow with the number of nodes. So that means that this weak identification issue is going to be getting stronger with the size of the network. So it's really like a standard weak identification issue. I mean, the X matrix is going to be weakly, the X prime X matrix is going to be weakly singular. So this, the consequence of that is that the variance components, which people are interested in the first place, tend to be biased. And so you all know about this particular bias correction of the residual variance. I mean, you know that by dividing the variance not by n but by n minus k, you get an unbiased estimator of the residual variance. You can extend this kind of correction to all variance components, and that's what was done in a paper in GRSSB in 2008 by Andrews and another by a bit later on. And then after that, other methods were proposed. A very famous one is the leave one out approach of Klein et al. And there is a new one recently that was proposed by students from TSC, Mireille Nascarate and Miguel Cerecero, which using resampling instead of leave one out, but at the end of the day, it's quite similar. So that was the first way to deal with the weak identification issue. You don't correct the estimates directly. You correct something, some aggregate statistics using the estimates. There is another literature where this issue of weak identification came acutely. There is in the graph, empirical graph literature, this so-called brown strand of literature that's called community detection. And spectral clustering is a way of finding communities. That is, you know that you don't have disconnected subgraph, but I mean, you want to isolate groups of nodes that tend to link within themselves. And if you have this weak identification issue is going to create spurious communities, and you want to correct for that. And so there is a very active, or there was a very active literature trying to improve these spectral clustering techniques. And the idea was to make the graph less sparse in a way that you had, by adding many links, you would remove the dangling subgraphs and by contrast keep only those which are related to the true communities. And so what they do is they take the adjacency matrix and they add. One way was to take the adjacency matrix of the graph that summarizes the links between nodes, and add a number, lambda. So that was one way. Then the Chin and Rowe very important for us paper, did something else. They take the Laplacian, which is a simple transformation of the adjacency matrix, and they only regularize this matrix D here, which is the diagonal matrix of the degrees, which is the diagonal matrix, such that every number on the diagonal is the number of links that one node, all nodes have with the other nodes in the network. And this approach has recently been shown to have some optimal properties for regularizing spectral cluster. And it happens, so that's the first insight in our paper. It happens that this way of regularizing the Laplacian is exactly what you do when you use a ridge estimation instead of OLS, a ridge estimator instead of OLS to estimate the two-way fixed effect model. So that's the first. That's a connection between a method that is used in statistics to robustify, in a way, OLS, which is ridge estimation. There is a connection between this way of regularizing graphs and ridge estimation. So, and then that brings us to ridge estimation with large dimension. There is a literature on that also. That's the ridge estimator. So that's how you have a weak identification problem. So this matrix is close to singular. You add something on the diagonal that makes the matrix less singular. And so by doing that, you increase the bias, but you reduce the variance of the estimator. It's a very well-known approach, and that relates to machine learning. There are two main methods in machine learning. There is ridge, and there is lasso. Lasso that would correspond to a particular way of regular. I mean, they are connected. So what this large dimension ridge regression approach does is that they consider a problem where the number of variables in X is very large, increases with the number of observations, and they study what happens asymptotically. But the setup they consider is one in which, by increasing, so for the model for the X prime beta of the model to remain finite, if the number of X's increases, you have to have that the parameters go to zero. So that's their main assumption. I mean, this approach is like they assume first that the variables are roughly uncorrelated, independent, and second, they assume that the parameters go to zero at the same rate as the number of variables, so that X times beta now is still computable. This is not at all what we have in those two-way fixed effects models, because what happens in this kind of setup is that a worker, most of the time, Dij is zero. Most of matches don't exist. So a worker will typically be matched with 1, 2, 3 firms in the period of observation. So, in fact, it's a very different setup, because instead of having a number of variables non-zero that increases to infinity, you have the number of variables that increases. But the reason why this is finite is because most of those variables are zero. So the parameters have no reason to change as a function of when the number of nodes increases. It's just that you sum only a limited fraction. A limited fraction of the variables. So you can't use this large dimension ridge. So what we do what I'm going to do quickly in this paper, the first thing I will try to show you. So I explain the what is the estimator. Second, I show you some simulations, and then I'll show you how we use some as the asymptotic theory that was developed for spectral clustering, and how this explains why ridge works and OLS doesn't work in our context. All right. So this is the model that I have written in matrix form. So W, so this is the vector of all worker effects. Phi is the vector of all firm effects. And W is a matrix of 0 and 1. That's going to be 1 if that selects that's that has the dummy variables for workers, and F has the dummy variables for firms. So we're going to keep the biggest connected component. We place ourselves in a setup where the number of workers is n, and the number of firms grows at the same speed as n. I mean, the US is bigger than France, and firms are not bigger in the US, so much bigger in the US than in France. There are just more firms in the US than there are in France. We typically have sparsity because the number of wages depends on the number of years of observation, typically 5 years. So typically you have 5 observations per worker. So if one worker changes employer once, I mean, that's a lot less. That's maybe 2-3 observations per match. So N, big N, that's the number of wage observations. Small n, that's the number of workers, and small p, that's the number of firms. We're going to get rid of any control variables, so by first regressing wages on, let's say, age, tenure, occupations, so that we have a variable that is centered. This is OLS. OLS solves this equation, and that's where you start to relate to the structure of the network. Is that when you calculate x prime x, in fact, that you get a matrix that is that has a block structure, which is quite interesting. Here you have a diagonal matrix where the elements on the diagonal are the number of observations per worker. df has on the diagonal the number of observations per firm. And B is just the matrix of dij. That's the number of observations per match for I and NG. So that's quite interesting. And then under which condition you can invert that. I mean, you can calculate this determinant, and that gives you that. And here, those who know about graph theory, they recognize a Laplacian. So there is a very strong connection between these two fixed effect regression and the graph structure. So it's a bipartite graph. So from the bipartite network where workers connect to firms and firms connect to workers, workers never connect to workers directly, firms never connect to firms directly. Still, you can induce worker graphs and firm graphs. You can say, I'm going to connect a worker to another worker if they have been employed by the same firm at some point. And I'm going to connect a firm to another firm if they have been employing a common worker at some point. And when you do that, you get 2 other networks that are standard networks with homogeneous nodes, and the Laplacian for those graphs have exactly the form that appears in the OLS regression. Same for firms. So given the time that I have, one thing about those Laplacians, don't read all that. I mean, just keep maybe the only thing that matters is the end. Suppose you keep one. So this Laplacian matrix is quite important because the first eigenvalue is always 0. And now the number of eigenvalues that are equal to 0 is the number of disconnected components. So once you keep only the biggest connected component, only one eigenvalue is equal to 0. And that just says that you have to make a normalization. One of the fixed effect for all workers has to be normalized, otherwise you don't have identification. So the typical practice is that you remove one, you normalize to 0 or something else. The parameter one worker fixed effect and one firm fixed effect, and that's it. And in principle, everything should work. The only problem is that if you have weak identification, many of those small eigenvalues are going to be close to 0, and this is what you want to control. So that's why we are going to consider this ridge estimator, where we add values on the diagonal of the X prime X matrix, and given that we have this is the vector of worker effects, this is the vector of firm effects, we are going to use two ridge parameters, one for workers and one for firms, and that's the formula for the ridge estimation. And what you recognize here is that it's quite amazing. It's nearly the same formula for the Laplacian that we had before, except that we have replaced those D matrices of worker and firm degrees by regularized matrices. What you do is that, in fact, you take the matrix of worker degrees and you add a lambda W. You take the matrix of firm degrees, you add a lambda F, and for the rest is the same matrices everywhere. So you keep a lot of the initial structure of OLS, and you regularize it in a very simple way. You can calculate the bias. So in the paper, we're going to consider something that we call the D-bias ridge, where we try to remove a bit of the bias of the ridge estimator, but not all of it. And in fact, in practice, it's improving things. So now what I want to do is progress in our understanding of what's going on. So in order to progress theoretically, you need a model of the network. You need to model network formation. And that's also useful to do simulations. So what we're going to do in the literature, there are many stochastic graph models. The most famous one would be the Erdős-Rényi model. And extending the Erdős-Rényi model is the stochastic block model, which assumes some heterogeneity among the nodes. And versions of the stochastic block models have been extensions of the stochastic block model have been proposed in the literature, in particular this degree-corrected stochastic block model. And that's, for some reason, I mean, this is a literature that appeared in physics journals. So what you do is you start with a number of workers, N0, and a number of firms, P0, and you divide them in communities. You assume that there is heterogeneity, and there is let's say, big K groups, and each worker has a probability pi wk of being in group K, and each firm has a probability pi fk of being in group K. So that's the starting point, the stochastic block structure of the model. And now you draw matches. So here we're going to do something simple. Either you match or you're not matched. Okay, so you could extend that, draw a number of wage observations per match. We're just going to draw whether there is a wage observation or not for match ij. And we draw that from a binomial distribution with probability Pij. And this Pij is very simple. It has this structure. You want to think of CKL as the probability that somebody from group, a worker from group K matches with a firm from group L. So CKL is telling us about how differentiated those communities are. So what is the probability that group 1 matches with group 2? It's going to be less than group 1 matching with group 1, but more or less. And once you have drawn the probability that the Ki is matched with Lj, you say which firm and which worker from that group. So what we're going to say is that conditional on a worker from group 1 matching with a firm from group 2, this particular worker of group 1 is uniform. 1 over the number of workers in the group. For firms, no. For example, we might want to say, once you know that you are matching with firms of group 3, you might want to say that a big firm has a higher probability of being drawn than the small firm. So you want to think of this as what is the probability of drawing one particular firm within the group once you have drawn a firm of that group. And C as this, it's essentially something that is a 1 on the diagonal, and then we have a small probability of drawing outside the small or less small probability of drawing outside the community. And then you can calculate the expected number of number of links between one firm and one worker. That's going to be exactly this matrix CKL. You can calculate the expected degree of firm J. You can calculate the expected degree of worker I. And just here, that's a remark that in their paper, Jungmanns and Wallner do asymptotic theory, assuming that the degrees tend to infinity. Here, we're not going to assume that because we know that the number of observations is fixed. So and that's what we get here. Yeah.
And so the use of the Pareto distribution is to match the Pareto degree of the.
It's to match the distribution of firms. The fact that we know that there are big firms. Very large firms and a lot of small firms. So that would be this idea. So then we draw worker and firm effects, and we want to think of the worker fixed effect as being something that depends on the group of that worker and plus a random component. There is a famous paper that appeared recently by Bonhomme, Lamado, and Manresa, where instead of assuming a continuum of worker effects, a continuum of firm effects, they assume that there are groups, and that there are only a finite number of worker effects for all the groups and a finite number of firm effects, one for each group. That would be just this part. So you can think of this model as encompassing both AKM, the standard approach with fixed effects, and the discrete mixture of BLM. And then we draw wages by adding a residual. So we assume normality, it's not necessary. So to make so first I'm going to show you some simulations. There is one parameter here that's important. Is so first, I mean, this what we put here, the relation between P and K, just something to get the formulas after. But the parameter that's important, the tuning parameter, is this small c. The bigger c, the higher the probability of producing a match. So the higher the number of matched workers and matched firms. So basically, the higher C, the more dense, the denser the network layer. So that will be the parameter that we vary in the simulation. So what I call P0 and E0, that's the initial numbers of workers and firms. And what I'm going to call N and P, that's the number after keeping the biggest component. Yep.
So the firm and worker effects are independent?
The firm and worker effects are independent, yes.
Okay, so there's no assortative making.
Yeah, well, there is through the probability of matching. But I mean, it's not the way you draw the fixed effect. You have your own fixed effect. You have your own ability. I have my own ability, and but maybe we have a higher probability of matching because I mean we are in the same group. So then when you calculate the covariance across all workers, there will be a correlation. So that's the way it's modeled in BLM and in my own papers. So it's that is, all the correlation is viewed as coming from the matching, the structure of the network, the matching probabilities. So that should please you, because I mean it's really there is economic decision behind the reason for correlations. Okay, so in those simulations. What I was trying to we are trying to target is a number of observations that is about the same, around 10,000 workers. So the sparser the network, the bigger the initial number of firms. So here we have 3 times more workers than firms initially. So N0 is 3 times the number of firms, and we had to simulate 3,000 firms in order to get 10,000 wage observations. At the end, we have 7,000 workers, 3,000 firms. So 7,000 workers here, about 5,000 workers in the you see here that the network is denser. So with fewer workers and fewer firms, you have more matches, and so you're going to have more wages. Sparsity can be measured as the number of links, matches, divided by the total number of possible links, which is N, the number of workers, times P, the number of firms. And you see that it's a very small fraction of all possible matches that are going to be observed. 0.05%, so 0.0005, something like that. It's a very small number. The average degree is around 1.5, 1.8 for workers, and around 3. So we are firms are on average relatively small, but there are some big firms. To get the parameters, we're going to use the rich parameters. We're going to use what is standard cross-validation. So we keep the last year. We estimate the model using in the data that's going to be like that. We're going to keep the last year, and we use the first, let's say, 4 or 5 years to estimate the model, and we try to increase prediction. For the simulation, that's not what we're doing. What we do is we simulate another network that we predict using the parameters estimated with the first network, and we try to maximize to minimize the predictive risk or the mean square error. And we find here in this example always something around 0.5 of the average worker degree or the average firm degree. That seems to be coming very often. The optimal reach parameter for workers is the same proportion of the average number of observations per worker or the average number of observations per firm, and this seems to depend on the size of the network. For 10,000 observations is going to be 0.5. For 500,000 observations in the true data that we use, it's going to be 0.05. So first, this is the variance composition that we get using these simulators. So this is the true composition. What you see is that the worker here, the worker effect would explain 42% of the wage variance. The firm effect would explain 14% of the wage variance. The residual will explain 31%, and the correlation between the worker and the firm effect, due to matching to the community structure, would explain 12% of the total variance. It's not far from what is usually found in the data. It's not by chance. I mean, we try to calibrate the simulation so that it corresponds to what has been estimated. Just one. We use 10,000 observations. Babet, Gaucho, and Palladino have recently estimated the AKMO on French data. They use the entire universe of wages, and they have 60 million wage observations for estimation. So it's not exactly the same the same sample size. But I mean, these simulations, I can do them on my MacBook. 50 million observations. I mean, it's a bit. I can use MATLAB, all in matrix, so it's fast. And for that, you don't really need that many data. So OLS. OLS is just crazy. With this network, then in this case, with a very sparse network, OLS is really enormously biased. The debiased OLS, so when you use, when you debias the variance components, it's still crazy. And this is what you get if you use the standard ridge estimator or the debiased what we call the debiased ridge estimator. I mean, these are two. So it's much better. Even in this very, very, very sparse network, we get something that is, in particular, this version of the estimator, which is a lot closer to the estimator. This is the outsample MSE, what you get for prediction in the cross validation study. You see that OLS is really bad at predicting wages in the validation sample. The difference between, so ridge would be the best by definition. The debiased ridge, you debias and you re-increase the variance, but it's not bad, not too bad. So this estimator is somewhere in between, much closer to ridge than the other one. So that's for C equals 1.
What if we select, after the ridge estimation, we select the phase effect that are different from 0, and then we re-estimate?
I mean, none are equal to 0. It's you get always something.
So it's not the same thing as lasso where we...
No. It's that's the thing. A ridge doesn't give you 0. I mean, it gives you. It compresses. It's it forces estimates to be closer to each. That's what ridge does. It's shrinking, whereas a lasso is removing some effects. And that's due to the penalization, which with ridge is the Euclidean distance, where for lasso it's the absolute value. For C equals 2, so we still have the same kind of true decomposition. OLS is still performing widely. the debiasing algorithm works very well. So that's what we found. I mean, debiasing works very well for variance decomposition as long as the graph is not too sparse in the simulations. In reality, given the huge amount of observations that people use, when you have 50 million observations, I mean, you can debias, it doesn't remove anything. So Babet et al., I mean, they see no difference whatsoever between the debiased using Klein leave one out estimator. I mean, it doesn't change anything. You get the same thing as the OLS estimates. And Ridge still performs in the same way. Standard Ridge not so good, not so well, but I mean it's not crazy. And Ridge debias works well. And when we see equals 3, it's even better. We always by increasing reducing the sparsity, you make OLS a better predictor of wages. So let's see now what you get in terms of the distribution of estimates, so that we understand. We tried so that we get a better understanding of why it is that the variance components are so biased. The blue is the true distribution of fixed effects. The blue distribution here is the true distribution of work. Here it's a firm fixed effects. So and the red, that's the distribution of OLS. So you see what OLS does is that, I mean, for many, you get a huge variance of worker effects. There is a lot of statistical measurement error in the estimation, despite OLS being unbiased. You have the variance that you get is huge. The dotted dashed line, that's the standard ridge, the initial ridge. What you see, you see the shrinkage. Okay, so it tends to and standard ridge tends to overshoot. This one here is the what we call debiased ridge. It works a bit better. No, I think there must be. No. Yeah. Okay, so that's. No, that's. Am I showing? Oh yeah. No, that's it. So here we have C equals 1. Here we have C equals 3. So in this case, you have a denser network, and OLS is indeed less dispersed than in this case. Yep.
So in a teacher value-added literature, the way to deal with it would be to do Bayesian shrinkage.
But that's rich.
So that's what you. So there's a
That's sort of that is rich. So what we do is we force and here what we have is that we plot the blue line, the blue dot, that's a scatter plot of the OLS estimator as a function of the true value. So that's the 45-degree line, and the red is the ridge estimator, and you see the bias. It's a bit tilted, and you see at the same time that what ridge does is that it reduces the variance a lot. So that's for the standard ridge estimator. And for, now this is the debiased estimator. Now you don't see the difference between between the distribution of the estimator and the distribution of the true value. And you see that when before it was a bit tilted, now we have removed the tilt. So what is more, that's what is annoying. With ridge, the bias tends to be in a certain direction. What you are getting here, you have larger negative bias here, positive bias, and negative bias there. Our debias ridge estimator remove this aspect. So this is for the worker the firm effect. This is for the worker effect. Standard ridge performs better than OLS, but we have this annoying bias. It's a bit tilted, and if you use the debiased ridge estimator, then the distribution of the estimator is right on top of the true distribution, and you have removed the bias. With C equals 3, you see that the variance also of the OLS estimator is much less than the dispersion than with C equals 1. Let me show you. So I'm going to go fast. That was spectral clustering. Even with C equals 3, spectral clustering works better with ridge, but it's still not so good. Anyway, I don't have time for that. Now, true data. We're going to use.
So the way the ridge estimator is working, you're implicitly reweighting things so that you're forcing the sparsest observations to have a sort of an average value. If instead you actually use the matrix itself to weight, so instead of putting just a bland lambda in that's constant across all observations, could you use the spectral structure of the adjacency matrix to figure out which ones to weight more and less?
So I thought about it, but that would be going. In fact, if you want to do that, that means that you want to estimate the network. So maybe you're using maximum likelihood, and so it's like a full-blown. You want to estimate the distribution of wages at the same time. That's essentially what BLM are doing. But I mean, maximum likelihood with fixed effects. I mean, it's not that easy to do. That's why BLM do first some k-means, some firms. But I mean, having these two-sided heterogeneity makes the likelihood quasi impossible to write. So in another paper with Rasmus Lenz at the moment, we're trying to use or some other techniques to get to that. But I mean, that would be what you might want to do. That is estimate by maximum likelihood or something else. At the same time, the structure of the network, the block structure of the network, and also the heterogeneity in the fixed effects. I mean, certainly, if you have a structure, if you have communities in the network, it's likely that you also have the fixed effect should be a function of these communities. And so there is the identification in wages at the same time as there is in the network, and you want to do that simultaneously. So, but here we are completely agnostic about everything. I just want to I'm just asking a question. Instead of using OLS, can you use something that is like OLS? It's coded everywhere, ridge, and is it going to work better? And then, do we have theoretical reasons to believe that indeed it's going to work better? So I'm not going to have time for that, but the asymptotic analysis aims at showing that the expected predictive risk is converging to something that is well defined when the number of nodes tends to infinity. So we have that. The next step will be to say, now what is the structure of this object? What is the optimal ridge parameter, like what they do in the other ridge literature? But that uses stochastic matrix theory by Marchenko-Pastur results. I mean, it's a very different issue. It already took us a very long time to absorb all that. Stochastic matrix theory, it's even something more. That's another thing. So we leave that to another paper. Here, these are the ADS, the French match employer-employee data. We're going to use so in this application, it was easy for me to use the data from for 95 and 2001. So it's a long time ago, but it's close to what Ebod, Kramar, and Margolis have been using. We do a lot of selection so that it can be done on a simple computer, and still at the end, that's something like 100,000 workers, 3,000 firms, and 450,000 observations. So it's a lot bigger. The average worker degree, so the average number of wage observations per worker is 4.7, nearly 5. And the number of wage observations per firm on average is 130. So there are some very big firms with thousands of observations, but on average, firms are small. The network is very sparse. Even sparser than what we had in the simulation, because it's the number of matches that we observe is only 0.04% of the total. But it's before it was 0.05. Now it's 0.04 in the true data. And because we have more data, the rich parameters are estimated smaller. This is the variance decomposition. Like AKM, we do find the negative sorting, negative contribution of the covariance. Debiasing doesn't make any difference. As I said before, it's about the standard debiasing from either using Andrew's formulas or Klein is the same. Rich gives you something that is quite different. Because we have more observations, the difference between Ridge and Ridge debias is gone. Nearly gone totally, and we do find a positive sorting. So on the true data, the Ridge estimation is producing a very different picture with some amount of. So we still have that the worker contribution is huge, 70%. The firm contribution is small, which is similar to what is found in other data set. And the covariance is of the same order as the firm effect. So it's very similar to what is found in the US and other. So there is something that's always been weird with the French data. We find the results that are more extreme than in other countries. This Ridge estimator brings the variance decomposition results closer to what is usually found. And this is what we estimate in terms of the distributions. So OLS, that's the blue line, and the Ridge is the other distribution. So for worker effects and for firm effects, and you do find you see that for worker effects it's not so different, but for firm effects it's quite different. OLS tends to find very large, extreme firm effects. So statistical theory in 10 minutes, good for you because it is certainly a bit boring. So I'll try to simplify. So these are the objects that we have to deal with. The symmetric Laplacian. The matrix of worker and firm degrees, the regularized matrices of worker and firm degrees, and the regularized firm Laplacian in its symmetric form is that. The first thing that you can prove is that by regularizing, you force the minimum eigenvalue of the regularized Laplacian away from 0. In fact, it's always you can bound the smallest eigenvalue by something that is always greater than 0. And the second thing that you can do is that implies that this matrix, which is 1 minus this one, is bounded from above. That's the first thing. So ridge regularization makes the I prime X matrix non-singular, and we can prove that. The second thing that we do is, what if instead of the true simulated, the drawn data network, what if we were considering the expected network? So instead of the matrix B of number of observations drawn for match ij, I was using the expected D, which is Pij, which has this particular structure that I have shown you before using this degree-corrected stochastic block model. And what if instead of the true degrees, we have the expected degrees? So you see, we have a network, and we're going to replace the network by the expected network. So instead, so a lot of the problem is due to, so yeah, that's what we do. So we respect the stochastic network by the expected network, something that we can understand the structure. And the structure is very nice. The expected network at all the structure that we are trying to discover. First, it has rank k. So the Laplacian is telling you how many the expected Laplacian is telling you how many communities you have, and it's telling you the community structure. And it possesses the same otherwise property that it is invertible, like the other one. And the main so what has started this study is this paper by Chin and Roy, and what they prove, and what this literature, Amini, other Bickel, and etc., some great names in statistics, they had figured out already that what is the link that there is between the observed network and the expected network. So let's try to calculate the difference between the two Laplacians, the Laplacian of the observed network and the Laplacian of the expected network. Let's calculate the distance between those two. So for that, you need a norm between the observed Laplacian and the expected Laplacian. The norm that is used is a spectral norm, that is the biggest eigenvalue of the matrix. That's one matrix norm. It's called the spectral norm. And what you can prove, so we extend that result to the bipartite graph that we have here, and we can prove that when you can contain the difference, so there is a way of choosing the ridge parameters. What this theorem is telling you is that if you let the ridge parameters grow to infinity, the distance between the observed Laplacian and the expected Laplacian goes to 0. There is a way of choosing a speed of convergence of lambda w and lambda f to infinity, and in fact it's very slow. You need lambda w and lambda f to grow with the log of the number of nodes. That's quite classical. A bit more, and as a consequence, with a probability that approaches 1, the distance between the observed Laplacian and the expected Laplacian go to 0. So the next thing that we do is that so how do you prove that is by using a version of the Bernstein inequality for matrices. I won't go into that. And then what we do is on retrousse nos manches, hein, and we extend that to the inverse of the Laplacian, because in the OLS estimator and in the ridge estimator, we have to take the inverse of the Laplacian. So you have to prove that by taking the inverse of the Laplacian, this result that you can replace the true Laplacian by the expected Laplacian still holds. So we have one theorem for that. We have a theorem for the unnormalized Laplacian. We have a theorem for this kind of matrices that. Why? Because, I mean, these are the matrices that appear in the formulas for the ridge regression. So the bias of the ridge regression depends on the unnormalized Laplacian and depends on this matrix here, which we have to control. The variance of the vector of fixed effects. I mean, you imagine a million of fixed effects, and the variance of that's a million by a million matrix. This matrix, we can prove that it is asymptotically equivalent to the matrix that you would get using the expected network instead of the true network. And then we can also, because look at the prediction, and the prediction itself is like what you would get using the expected network instead of the true network. And that's. I believe that it goes in the direction of understanding why ridge is going to work better than OLS, because you can't prove that for OLS. If you want to prove something like that for OLS, you have to assume that all workers have a number of observations that tend to infinity. This is what Jungmans and Wiener do, which is never the case. Voila, so I'm about done. So those conclusions, we're on the way of understanding why it is that first how you can improve standard estimators of the variance. Okay. Question.
So yes, I'm not asking for a proof, but in practice you're going to be using cross-validation to prove the tuning parameters, and your theory requires that the tuning parameters diverge to infinity when the sample size increases. Do you find empirically that if you do, in your application, if you restrict the DADS to like 1,000 workers, 10,000 workers, and you find that in practice the cross-validation parameter tends to increase with the sample size?
What we do is that we compare what the values that you need for the parameters, the regularization parameters, with the DADS to what we found in the simulation. We didn't do an extraction of a smaller sample from the DADS. We could do that. I mean,
it's a bit unusual not to require that the tuning parameter goes diverges, no?
It's always like that. I mean, you always have to and I mean, in standard ridge. In standard OLS, x prime x is of the order of the number of observations, because what you do is you divide x prime x by n. Okay, so that means that x prime x plus the lambda has to be proportional to n. So in standard ridge, the ridge parameter is of the order of the number of observations. Always. Here it's much lower, and that's due to the fact that x prime x here, the highest eigenvalue is bounded by 1. It doesn't diverge. So it's really different from the standard setup. So it's,
I'm a bit confused about the fact that you say that your method is more fitted to the DADS because of the random matrix theory supposes that the size of the matrix should go to infinity. But with random matrix theory, you don't need super large, you need large matrix, but DADS seems to be like enough large to meet the asymptotic distributions of the Marchenko-Pastoro methods.
So, except that, I mean, we are not in a standard Marchenko-Pastore setup. So the x prime x matrix doesn't go to infinity. The eigenvalues stays between 0 and 1. So it's quite a different setup than the standard ridge, a large dimensional ridge theory.
So if you do x prime with the GLDS, and then you don't see like a match.
So we do see that the distribution of eigenvalues, indeed, when you increase you reduce the sparsity, then it becomes more like the standard Marchenko-Pastor distribution. Yes. So in the case of C equals 3, I can show you that in the simulation, we find something that looks like a Marchenko-Pastor distribution. For C equals 1, not at all. And still, it seems to be working fine. So fortunately, we don't need the regulation parameters to inflate as much as what. I mean, this theory is very conservative. I mean, in order to get a result, I mean, we cut with a very big, very big knife. So, and that's true always of asymptotic theory. Unfortunately, asymptotic theory is like using gloves to peel whatever. Yeah.
I was curious about the fact that you find that for the French GLDS data, the ridge makes a big difference with the OS.
Yeah, me too.
And you say we get back to the same kind of results as in other countries. So either it's in other countries there's no big difference between the ridge and the bias, but if it's that, or it's that, it would also be different.
Yeah, so I hope that this paper will generate a lot of.
The GLDS data that would make it likely that there are different, like more sparsity than in other contexts?
Frankly, that I don't know, because since the beginning, they estimate a negative sorting. They have a hard time get zero sorting. So, and they need huge data. So, and it's only recently that it works better. But the DRDS from the 90s, I mean, it's terrible.
On the German data, there's no negative sorting. The IAB.
Yeah. I think it's IAB. I don't know, but usually it's slightly positive. It's not big on the American data or on the Italian data. So France, it's special.
Did you look at the decomposition of the network for the French data? But maybe in France, like there are maybe more communities that are more disconnected.
Could be, but I mean, you can't. These are good questions. So I think nobody has used spectral clustering to look at study those networks. And in fact, nobody anywhere. It's kind of weird that nobody's tried even using US data. And so in this literature, it's all about variance decomposition. So, and it's all about bias control. So we have formulas for the bias, and then we're going to spend a lot of time trying to find another algorithm that asymptotically gives you the same thing. That's what Klein does. I mean, the leave one out is just one way of doing the same thing as the formula. So, and I mean, are there computer gains in terms of computer times? Well, so there are some gains. They can deal with heteroscedasticity, but you can adapt the formulas to deal with heteroscedasticity either. So that's what the literature has focused on until now. Not so much on the structure of the network. What BLM and what we do in the paper with Rasmus Lenz and Suphanil Piyapromdi. I mean, we look at the network at the same time as we look at wedges, but at the cost of assuming that there is no residual in the equation for worker and firm fixed effect. So it's a pure discrete mixture model. This is going back to the continuum of worker and firm fixed effect. But I think we're done with time.